Hello, everyone. In this video, we're going to look at another example of applied optimization coming from section 2.9. And as just a reminder, I'd like to encourage you to pause the video and first try to work out a solution on your own. And after you've had some time to think about the question and work out a solution, then please continue watching and we'll look at it together. All right, so for this problem, we are told that a company sells Q ribbon winders per year at P price or P dollars per ribbon winder. Then we're told that the demand function for ribbon winders is given by P equals 300 minus 0.02Q. So this demand function tells us if we have Q, the demand, the price of that of the items given a certain demand. So now we're told the ribbon winders cost $3 a piece to manufacture, plus there are some fixed costs of $9,000 per year. Recall, fixed costs are those costs that are associated independent of how many ribbon winders we make. So we want to find the quantity where profit is maximized. So if we zoom in here on the question, quite literally zoom in, we want to maximize profit. So in order to do that, we need to write a profit function. So let's just recall profit is the amount of revenue, how much money we're bringing in, minus the costs, how much money it takes to produce the items. So in order to write profit, we need to first find the revenue and cost functions. So revenue. And because we're looking at price here, we want to find the quantity where the profit is maximized. So that's actually a quantity here that we want to determine. And we have price in terms of quantity. That means we want our revenue function, our cost function, and ultimately in the end, our profit function to be a function of Q, our quantity. And again, that's coming from this language here because we're asked to find the maximum profit associated to a certain quantity. So we wanted to find the revenue as a function of quantity. Well, revenue itself is a function of quantity and price. But do we have a relationship between price and quantity? Heck yes, we do right here. So we know the price is equal to 300 minus 0.02Q. So what we can do is substitute that in to our price. And so we just have revenue in terms of quantity. So revenue in terms of quantity would look like Q times 300 minus 0.02Q. So there's our revenue function. So now we need to find our cost function. And ideally, we want to find the cost function in terms of quantity. That is quantity produced. Well, how are we going to determine that? Well, let's look at that information they gave us. They said that it costs $30 a piece to manufacture a winder. So if we make Q winders, how much money will that cost? Well, we'll pay $30 per winder, so 30Q. But then we also have a fixed cost, 9,000. So we're going to add 9,000 no matter what, no matter how many quantity we make. So then our cost function, C of Q, is 30Q plus 9,000. So lovely. Now we have our revenue and our costs. So now we can write profit as a function of Q is revenue. So Q times 30 minus 0.02Q minus cost. So we subtract 30Q plus 9,000. So at this point, if you didn't compute this profit function on your own, or if you weren't able to get here, please pause the video and try to simplify this function before moving on. All right, and then we'll simplify together. So what happens here, that Q is going to come into both terms. So we get 300Q minus 0.02Q squared. And then remember this negative is also going to come into both terms. So then we get negative 30Q minus 9,000. So now let's go ahead and combine like terms. I see some Q's here, 30Q minus 300Q rather, minus 30Q. So we get 270Q. Then we just have our squared term, so minus 0.02Q squared minus 9,000. All right, so now we found our profit function as a function of Q. I'm going to go ahead and highlight that so that we have it. Okay, so we want to maximize this profit. So to do that, we need to find the derivative of our profit function and find the critical values of that profit function. So we need to compute P prime of Q. So just taking the derivative of each term, we get 270 minus 0.02 times 2Q. That's just the power rule. And then plus 0 if you'd like. So that just becomes P prime of Q is equal to 270 minus 0.04Q. So now we need to find those critical values of our derivative. So no Q here will make this function undefined. All Q's work. So we just need to find the zeros. So where is this function equal to 0? So we can set 0 equal to 270 minus 0.04Q and solve for Q. So I can add 0.04Q to both sides. And from there I get, press the wrong button there. Okay, what's happening? There we go. Okay, back on track. So from there we get 0.04Q is equal to 270. So dividing both sides by 0.04, we get Q is equal to that quotient. So let's compute that together. So taking us over to my calculator, 270 divided by 0.04 gives me 6,750. All right, so that's my testing, or that's my value, that my quantity that we are going to determine if that quantity is actually our maximum. So a couple ways we can do that. The way that we've been determining if a critical value is a max or a min is to find the second derivative. So we could do that, P double prime of Q. We just need to take the derivative of P prime. So that's going to be 0 for the first term, and then just minus 0.04. So no matter what Q we have, we're always going to get a negative, which means we have a concave down function, which means at that point we found, that critical value, that horizontal tangent line, will be a max. We could also just go back to our profit function and recognize that this profit function is a quadratic function. It has this squared term, and the constant on that squared term is negative. So yep, we have a concave down function. All right, so now we can summarize here and also make some room for ourselves. So we're asked to find the quantity where profit is maximized. So we can say the profit is maximized when we have Q equal to, or quantity equal to 6,050. Awesome. Great work, everyone.